So as we talked about in class today, the universal law of gravitation tells us that if we've got 2-point particles, here's a point particle of mass 1, here's a point particle of mass 2, they're separated by a distance r, that there's going to be two forces in this problem. There's going to be the gravitational force that mass 1 feels caused by mass 2, and the gravitational force mass 2 feels caused by mass 1. Both of these forces are going to be directed along the line joining the two particles. They're both going to be attractive, so you can see that the force mass 1 feels is attracting it towards mass 2, the force mass 2 feels is attracting it towards mass 1, and that both of these forces are going to have a magnitude that's given by this expression. So the magnitude of the gravitational force is going to be big G times the product of the masses divided by the square of the distances. Big G, again, is this value, and we'll leave it in these units for the moment. So all this we talked about today in class, and so what we want to do is we want to sort of transition and basically talk about, well, we dealt with the gravitational force all last semester in 298. We just typically dealt with it in this form, so that we said the gravitational force of someone on or near the surface of the Earth happens to be given by mg. So again, this was the mass of the person, and just haha, person not to scale, right? So here's the person standing on the surface of the Earth, so this mass would be the person's mass, and then g was the gravitational acceleration. Well, if the universal law of gravitation is going to be universal, then it also has to give us this expression. And so what we're going to do is say, well, for starters, the universal law of gravitation applies to point particles. And the person here is probably not a point particle. The Earth, in this case, is clearly not a point particle. So for starters, how can we use this expression? Well, it ends up that what we can do is we can basically break both of these masses up into tiny little masses that act like point particles. And then we just have to sum over all these point particles that you've broken the Earth up into and all these point particles that you've broken the person up into. And what you get when you do that, and it happens to be a fairly nasty calculus problem, but what you get when you do that says that as long as you're outside the surface of the Earth, then you can act like the entire mass of the Earth is located at its center and then treat it like a point particle. You can do the same thing for the person. You can act like the entire mass of the person is located at the person's center of mass and then treat them like a point particle. So the distance of separation then for a point particle that's going to represent our person and the point particle that's going to represent the Earth happens to just be one Earth radius. And so what we get is when we use the universal law of gravitation, we get that, well, here's our gravitational constant, big G. We got mass of the Earth, that's one of our particles. It's located here. We've got mass of the person, that's our other particle. It's located here at the surface. And then the distance separating the two of them is the radius of the Earth, so that gets squared. When you pull the mass of the person out front, what you're left with is big G times the mass of the Earth over the radius of the Earth squared. And so what these two equations tell us is since they're both a way to calculate the weight of a person or the gravitational force acting on a person on the surface of the Earth, we've got to be able to set these two things equal to each other. So little g, our gravitational acceleration, has got to be equal to big G times the mass of the Earth over the radius of the Earth squared. And so if you happen to take the mass of the Earth and just sort of an average Earth radius, take the gravitational constant, plug it all in, sure enough what you get happens to be 9.8 meters per second squared. So using the universal law of gravitation, and just again, for the moment we're not going to worry about the details of the calculus problem, but the calculus problem that tells us it's okay to treat these two masses as if they were point particles located at their centers of mass, gives us exactly the expression that we expect for the gravitational acceleration on the surface of the Earth. So what this means is that we can calculate the local gravitational acceleration in some sense anywhere by simply treating m as the mass causing the acceleration and then treating r as the distance from the center, the distance from the distance you are from the center of that mass causing the acceleration. So this we can now think of as the local gravitational acceleration. That's just going to be gm over r squared in magnitude. So if you want to talk about the local gravitational acceleration on the moon, well, now here's the moon. We're going to act like the moon, all of its mass is concentrated at a point particle at the center. Some astronaut standing on the moon. We're going to act like the mass of the astronaut is a point particle here at the surface. So the mass causing the gravitational acceleration is the moon. The distance between where you're interested in the gravitational acceleration and the center of mass of the moon, that happens to be the radius of the moon. And so we plug in those values, calculate it out, and happen to get 1.6 meters per second squared, which happens to be about 1/6 of what it is here on the surface of the Earth, which is what the gravitational acceleration is equal to on the surface of the moon. So one of the things that you notice here is that the gravitational acceleration, even though we still have the astronaut drawn in the problem, the local gravitational acceleration doesn't care about the astronaut. And that's an important concept that we'll talk about going forward. If you want to talk about the local gravitational acceleration at some height above the surface of the Earth. So now, again, the mass causing the acceleration is going to be the Earth again. But your location from the center of mass of the Earth is now the Earth's radius plus some height above its surface. And so that's what our little r now is. That's the distance from the center of mass causing the acceleration is now the radius of the Earth plus your height h. And so when you plug that in, you get this expression. And so now tell me how high we are above the surface of the Earth, and I'll tell you what the local gravitational acceleration is. Given what the radius of the Earth is, if I don't have a height that's fairly significant, at least in terms of some substantial fraction of the radius of the Earth, then I'm not really going to do anything to affect the value of the gravitational acceleration, which is why when you climb up some mountain, even though that may be a fairly high mountain, you still haven't radically changed heights relative to what the radius of the Earth is, which is why you don't feel significantly lighter. The gravitational acceleration is not radically different.